these are very, I mean, there's so other, like a lot of other information on the website. I mean, I don't suppose I've seen like this anywhere else. So yeah, thank you, Asif. Like there's a lot of information like out there.
Thank you, Prachi.
Asif, I'm sorry, I'm interrupting again. Yeah, you're streaming it because Balaji might not be able to attend today, so he wanted you to request to like stream it on live on YouTube.
Yes, in fact, I just did. I'm sharing the link. It is live now on YouTube, and I'm putting the link on our live.
Yeah, thank you.
I put the link of the YouTube, and it's being live broadcast. All right, guys. So with those preliminaries, I
So
guess
Asif, when are we planning to start time series?
I'm going to do it not the next week, but the a week after that, quite likely.
So, Asif, what is the agenda for this Wednesday and then next week?
See, this week is on anomaly detection, which is a pretty large topic: outliers, anomalies, fraud, and so forth.
Yes.
Right. Next week, I'm going to squeeze multiple topics into it. One day, I'll do the explainable and the interpretable aspects of AI. And the other day, and include a lab also, short lab on that. And the other day will be on neural architecture search and hyperparameter optimization. In other words, automated machine learning, automated AI. Then after that, we'll move on to time series and see how much time that takes. Remember, guys, this is a workshop on deep learning, so I'll focus on the deep learning aspects of time series. And that should take some time. Then, so let's take it as it goes. I'll try to squeeze in as much as I can because you all seem to want me to squeeze a lot of stuff in.
Yeah, no, because if you're planning to put 2 weeks, then your object detection will be dropped.
Yes, I don't want to drop that. CNN is very important. So we
So it
will
looks
see
like then you're dropping the time series, like a day, week of the time series.
Yeah, so we will do, let's see how long the time series takes, right?
So if you
Anil,
do
this is
like
a
this week
workshop.
or next week, yeah, that way it would have been better.
See, Anil, let me be very clear. Huh? This is a
Yeah.
workshop on deep learning. So
Yeah.
I will cover time series from a deep learning perspective, right? Time series otherwise is a broad topic. It will take us 3-4 months to do time series. People spend a lot of time. So I'll cover as much as I can of the foundation, and I'll cover the deep learning aspects, right? So let's take it as it goes and see if it meets everybody's expectations. But leaving out object detection is a terrible idea. The whole things like self-driven cars and other things, they're all premised on the theory of object detection. It's very important. So we need to do that also. We need to do, you guys want everything essentially, the automated machine learning, the interpretable AI, and so on and so forth. So we'll see how fast we can go and how much we can cover. All right, guys. So with that, I would like to start the recording now. All right, guys. Today's topic, or this week's topic, is anomaly detection. It's a huge topic. There's a whole industry around this topic. It has to do with finding outliers in data, finding novel features in data, finding fraud detection. And fraud detection is a hugely important topic. The reality today, from a practical perspective, is that, for example, essentially fraud is winning. Everywhere you hear, for example, this week itself, we heard to our unpleasant surprise that some critical government departments have been hacked, right? So it means that the anomalous traffic that we got, network and login and so forth, the traffics that we got are things that happened, went unnoticed, and the hack could happen. So to observe the network traffic, to observe user behavior, to observe all sorts of things, data about financial transactions, data about medical, medical data, for example, the presence of anomalies in somebody's x-rays, all of it put together makes for a very vital topic or tool in machine learning, in our, whose which it is hard to exaggerate the importance of. It is used everywhere. It is also a topic that is really worth doing. People who can do this can become good at this field. Generally, you can join companies where just this one topic will keep you entertained for the rest of your career. So it is a very important topic. We have done some part of anomaly detection in the past. Those of you who attended the boot camp last year, we did 1 day of anomaly detection. In particular, we did the classical methods. We did not use deep neural networks for that. So the way I will do today is I'll broadly talk about the concerns of anomaly detection from first principles. Then I'll talk about some of the classical methods. It's worth quickly going over them, what those are, and then coming to deep anomaly detectors, or DADs, as some people call them. Now, the good news is the deep anomaly detectors did prove in many ways, in many areas of anomaly detection or fraud detection and all of that, it proved to be a game changer. It led to much better performance than the previous models that used to exist. So that is, therefore, it is important to know this topic very well. We have a substantive lab coming up on Wednesday on this topic. And so that's that. Now, there is another bit of good news, which I suppose it's time to reveal now. It turns out that I've already laid the foundation for anomaly detection using deep neural networks. In the previous sessions, in the previous weeks, I was sort of building up to it. You notice that I covered auto encoders, and I sort of insisted we do it and not miss it. One of the big reasons I did the auto encoders is they play a central role in anomaly detection. Right? Likewise, we covered GANs, generative adversarial networks. GANs are another means to uncover anomalies. We will study these two approaches in the deep learning, and we'll look at all sorts of hybrids and variants of it. For example, there is a Ganomaly, which takes a GAN and autoencoder, and by a conjunction of the two, it comes up with a fairly good anomaly detector. So there are various architectures that we will encounter. But given the fact that you all have a background now in autoencoders and in generative adversarial networks, our going should be pretty smooth. Right? So I'm hoping that this broad topic of anomaly detectors, the entire theory, I should be able to cover today. Right? Now, I was uncertain whether I would bring in anomaly detection into this workshop, since so many topics need to be covered in the ensuing weeks. But there seemed to be quite a high demand for this. So therefore, I'm covering it. And I apologize, given the compacted nature of this workshops. We had just an 18-week workshop. The time that we can give, once you realize its importance, one can start wishing if we could give more, perhaps a month to it. We won't be able to, though. My hope is that in some sense, we have given a lot of time to it. We have given weeks to, we have given a week to generative adversarial networks. We have given a week to autoencoders. So in some sense, 2 weeks have already gone into it. This could be considered the third week of anomaly detection from that perspective. All right, so with that administrative aspects out of the way, let's get started with anomaly detection. Give me a moment. I'm just pulling my writing pad towards me. So our topic is anomaly detection. This also goes under the name of outliers, outlier detection, and related terms, for example, novelty detection. And there are subtle differences between outlier detector and novelty detection. And we'll talk about it, though broadly speaking, they all come under the same umbrella. They're quite close, they're very close cousins of each other. So we'll talk about that. Now, when you look at anomaly, first way to think about it is to think in terms of outliers, right? Or anything that sort of is not representative of normality in the data. So this brings up an interesting concern. How do you know that something is an anomaly or it is an outlier? It is an anomaly or an outlier in the context of some other large amount of data, which is not anomalous and which is not outlier data, isn't it? If you had just one data point, you wouldn't know whether it's an anomaly or not. It is one data point. But when you have a lot of data points, and those data points show a certain pattern, a certain distribution, and this element stands far from the distribution, its likelihood of happening is low. Then you say it's an outlier, it's an anomaly. So the history of outliers and anomaly, the theories have been pretty long. Starting with basic statistical definitions. For example, there is a definition, I believe, from the mathematician Tukey, which dates back to a long time, which basically says that for one dimension, if you, so suppose you have, obviously most distributions are not necessarily Gaussian, but to are bell curve like, but for the sake of keeping it simple, let me say that it is. You have a mu, you have a sigma, the width of the bell curve, right? And Tukey said that, see, most of the area, as you can see, the mass of it is between minus, this is mu minus sigma, this point, mu minus sigma, and this is mu plus sigma. So you can clearly see that the mass of this, sort of the bulk of the mass of this is between these 2 points. Let me call this point A and B. So one easy way that I often say to visualize this is, imagine that this is a sand hill. If you were to think of it as a sand hill, you would agree that most of the sand is in the yellow area, right? So that is the quintessential definition of inliner data. Inliner data. In other words, that is the core of it. That is how it should be, quite representative of it. Then by the, and I believe for a normal distribution, you can look up the number, I believe is 68%. Right? Then you can go one more standard deviation, and I believe that will take you somewhere here, mu plus 2 sigma, and here, minus mu, oh sorry, mu minus 2 sigma, this point, AB, let me call it C and D. And then we have the area that is here and here. We say that so let me just give it a legend. This region is inliner data according to Tukey's definition. Then he went on to say that let's treat this as sort of not big outliers, like soft outliers. It's beginning to get outliers because outliers is ultimately a subjective term. So let's call this soft outliers. And then you go to the third standard deviation here, this point. This is mu plus 3 sigma, and this is, and one of you please look up the exact numbers, what is there, because at the top of my head I don't seem to remember. I think by the time you cover the region that is yellow and red put together, you're already looking into the 90s. 90%, 90 plus percent of the, sorry, of the mass is already of the sand hill is already present here. Now, if you include this, and one of you, if you have a chance, look up the bell curve and the 2 standard and 3 standard deviation. Let me know what these numbers fall to. Right? I believe first is 68, the second is in the 90s, and the third is in the high 90s. So by the time you include
99.7.
Come again?
99.7, I think, for the 4.
99.7, yeah. Okay, so actually, I take it back. I think Tukey called both red and yellow as inliners. I believe he started calling it, I take this back. This is not, this is also by Tukey's definition. I think this is also inliner data according to him. And then the green becomes your soft outliner. And you know, these are matters of definition. It turns out, I just realized that my recollection may be flawed. Soft out.
There's like 4, past 4 is the hard outliers, right?
That is right. And then everything beyond that, you can start taking beyond. Right? You are looking at outliers. And beyond 4, of course, or beyond 3, outliers are definitely beyond 3 and 3 sigma. And then beyond that, it is very clearly an outlier. So for example, if you got a standardized test score and you were 3 standard deviations above the average, you have a very, very high percentile. I believe it's somewhere around 99 or 98 percentile at 3. Okay, did you look up the numbers?
Hold on a sec.
Okay, so you can let me know. So this is it. Now, this is correct with respect to, this is easy when you have one-dimensional data. But even with one-dimensional data, things do get complicated. What if your distribution is like, it's not very clear, it's like this. So the question is, at what level or where do you start deciding that it is an outlier? If you have a distribution like this, where do you start saying it is an outlier? So you realize that so long as your data has a normal distribution, it is a lot, this whole way of defining soft outliers and hard outliers and outliers, etc., sort of fits with our intuition. But when the distributions start having very long tails, now what would you call an outlier? This tail just goes on and on and on, right? For example, when you look at the shopping, consumer bestsellers or the items sold by Amazon and how many instances of the items were sold. It can be long. So things begin to get a little bit uncomfortable, but still people, one dimension is relatively simple. Now what happens in 2 dimension, that's where, and 2 and higher dimension is where the story begins to get more interesting. Suppose you have data like this. And this is the bulk of your data. Now, what about this point A or this point B? What can you say about, and what about C? Let's ponder over A, B, and C. If you just look at the distribution here, like along the axis, maybe this will show some form of normal distribution. So C will stand out. If you look along each of the axes, probably C will stand out, isn't it, guys? Right? Because C will fall somewhere here, and it will project itself somewhere here on the y-axis. So this is the y-axis, and let's say the x-axis, right? What about A? Do you think A will stand out? A seems to be falling here, here, and B seems to be falling here and here. So the question therefore arises: how do you discover that A and B are outliers? So the first thing is, of course, you realize that they are outliers. They're broadly outside this sort of dense envelope that I made for the data. Are we together, guys?
Yes.
Right? So we have that. So you realize that one-dimensional intuition doesn't easily move forward to 2 dimensions or higher dimensions. Right? Or you can miss a lot of outliers if you use a simple reasoning like that. And therein lies the complication. Not only that, what if the data came something like this? You had regions, like for example, we keep talking about cows and ducks. So here are your ducks in the size, weight, scale. And here are the cows, big and heavy. Let's say somewhere here. So now you realize that this particular A and this particular cow, B, you would like to call these outliers, isn't it? Right? This A is a rather overweight duck, right? And B is a rather underweight cow. You know? So it is an anomalous in weight. A and B are both anomalous in weight. And of course, I could have gone in the other direction, in the size direction, or I could have put, I mean, any one of these places. So what is your intuition? You see that these things are away from the dense regions. So now I'm going to say that we have a way, we have been learning a lot of techniques along the way that we can repurpose to discover these outliers. Can you think of some of the techniques, guys? What can we use?
So Asif, can we use density based?
That is right. We can use, and more broadly, so suppose we use density-based clustering. What does it do? Remember, one of the things that density-based clustering does, dbScan, DenClue,
Or DenClue? Yeah, I think we can use DenClue.
etc. All of them will create an envelope. You set a threshold of density. Points beyond that are declared as outliers automatically. So density-based clustering, one of its side benefits is that it produces for you these outlier points as a side benefit. Then you can do even other forms of clustering, any form of clustering. Suppose you did k-means itself. So let us say that the k-means did this entire partition, it called duck. And this particular partition, this side of the feature space, it called cow. Even then, all is not lost, because what you can do is you can go to the center of the cow and the duck, the centroids, and just look at the distance, observe k-means. K-means, you can say clustering. So let's say this was number 1, this is number 2. What you can do is k-means, you can go to find the centroid, distance of a point X to centroid, whichever centroid it belongs to. Are we together? So if this distance you compute for all the points, you will then get a one-dimensional. We are reducing the problem to one dimension. What will happen is most of the distances, let's look at this ducks here. Ducks. This is the mu of the duck. And what will happen to this duck? Right? The distance from the centroid of A will be here, right? It will be far off. This is where the A will fall. In terms of this y-axis, this is distance. Are we together, guys?
Yes.
Does it make sense? Most points will be close to the centroid, and they'll have some sort of a tapering off density or proportions or probability density. But A will be literally standing off as an outlier. Now you can broaden it to any clustering, whichever means of clustering you find, whether it's k-means. Now it's easy to see that you can generalize any because the moment you discover clusters, you can find centroids, right? Just need to centroids. But then you have the extra step. In DB scan, outliers come free. So outliers come as a free byproduct, isn't it? But if you use any other form of clustering, then the burden is on you to get the centroid and to compute the distance, to plot it out, and so forth. So typically what happens is the further you go, the more you feel that it is an outlier. There are many metrics to tell whether something is an outlier or not, like local outlier factors and this and that. I will just use one particular metric, which is just called S of X, usually denoted as S of X in the literature. It is called the anomaly score. Now, S of X belongs to the interval 0, 1. So closer to 0, it is not an anomaly. Small values, not an anomaly. Right? Large values, large is relative, of course. It goes from 0 to 1. Anomaly, right? So you can choose a cutoff. Let's say that you can say, I will take 0.5 as a cutoff, right? And now what happens is that people have standardized as some one score. Just tell us one score so that we can tell. And people who implement these algorithms for anomaly detection, they ultimately come up with some way of producing a score that is between 0 and 1. And there are many, there's a bit of mathematics associated with all of them that you can use. We won't go into all of them. It all agrees with intuition, basically. So it's not, we'll move a little bit faster, as I said, and stay on the big topics because we need to move faster. So therefore, you realize that you can use clustering. So what is a realization? We can use all sorts of, number one realization, one, clustering. Algorithms, isn't it? Or clusters. Number two, this is one. Then comes an interesting fact. What else can we do? Just look at this data, cows and ducks. What else can we do? So what happens when you are an outlier? would it be reasonable to say that your distance to neighbors is pretty high? So suppose you are an outlier here, this point, its neighbors is this, 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 right? So do you notice that these distances are pretty large compared to inliners? Inliners seem to have neighbors very close to them, but outliers tend to have neighbors rather far from them, isn't it, guys? So you could, for example, say, I will look at the average of the K and N distances averaged to tell. That could be one way of deriving your anomaly scores. Now, it doesn't always work. The trouble with these naive approaches are they don't always work like KNN. Why? Because you may have a distribution. Let's say that you have data. Most of the data is here, and some of the data, just a tiny amount of data is here. You want to treat this as anomaly and this as the inliner. So will your KNN work for you? Would anybody like to say, would KNN work in this situation in detecting the anomalies?
You mean when the anomalies are a close cluster themselves?
Yeah, exactly. They are closely clustered in themselves. And that just alludes to the fact that quite often you have to try things out, ultimately know the distribution of the data before you can choose which particular algorithm to use. Now, there is another thing to it. Suppose I give you clusters based on this same idea. How could you have solved this problem? What you could have said is, you could have done clustering and you could have called it cluster 1, cluster 2. And you may just notice that cluster 2 is way smaller than cluster 2 is much, much smaller than cluster 1. The number of elements in cluster 2 is much smaller than the number of elements in cluster 1. That itself is indicative that it's an outlier or anomaly, isn't it, guys? Because this big, large cluster is inline data, and relative to its C2 is the anomaly or the outliers. So that's how you argue with outliers and anomalies. There are many, many algorithms that you can repurpose for that purpose. Right? Now, let's try something else. You could say, hey, why not treat this as a classification problem? Let us say that, so you realize that these were all unsupervised learning methods, right? We are applying KNN, we are applying clustering, right? Average KNN distance or clustering, right? They fall uh, under the general category of unsupervised learning. Why do we call them unsupervised learning? Because the data doesn't come with a label saying this is inline data and this is outlier data. Right? But then let's go a little bit further. What if it was? What if you could tell that this is outlier data and this is inline data? So for example, consider a credit card fraud data set. This is a fairly used data set that, Harini, I think you did a notebook on it just now, isn't it? So,
Yes, sir.
yeah, and so the idea is that there are a lot of transactions that took place in Europe in a certain year, and a few of them are fraud. So you get a transaction X and you get a Y, right? Data comes like this. This belongs to either a fraud, not a fraud, or a fraud, right? It can take one of these two values, right? Now the idea is the fraud is, in some sense, in the feature space, you would imagine that it is an anomaly, right? It cannot be the normal pattern of behavior. Obviously, the fraudsters would like to make it look as normal as possible, but there must be some vector space, some feature space in which the fraudulent transactions stand out. isn't it? And can be separated from the good transactions, the non-fraudulent or the valid transactions. So that will bring up the question, why not just use a classifier, right? So would somebody like to put some thoughts into it?
You don't have enough data, right? The
You know,
anomaly occurs very rarely.
that is one
How you
reason.
learn
Yes,
from it.
class imbalance. That's a good point. Typically, data that is anomalous can be, there'll be a huge class imbalance situation. By definition, it's an anomaly, so there can't be too much of it. And sometimes it's extreme. Sometimes you have very few incidents of it, right? And so the question is, can you detect it if in your data set of 1,000,000 records you have, let's say, I'll hypothesize, just 10 records or 20 records that are supposedly anomaly, right? So for rare diseases, that's very true. Some rare diseases by its very name means uh, when you gather data, very, very few people will have those rare diseases. So you capture a lot of feature. You know that in some place in the feature space, these two things separate out. There exists some vector space where the disease person, the people with that rare disease and the people without it, the normal people, their biometrics will separate themselves out, right? Except that you don't know it. And the data point is very small. So when you apply a classifier, you have to be sensitive to huge class imbalance, a massive asymmetry of data. Now, there are methods to address the asymmetry of data. If you naively apply logistic regression or any one of the classifiers, a random forest or whatever it is that's your favorite classifier, you will end up in trouble. You will miss a lot of either miss a lot of anomalies, or you will start classifying a lot of normal data as anomalies, right? So you will have a lot of false positives or false negatives, right? Both sorts of errors will keep cropping up. We went through this exercise. Those of you who participated in the boot camp last year, you realize that we did this as an exercise. So then you say, well, wait a minute. There are techniques to address imbalance in data. If you remember, we used some libraries.
Yeah, the resampling method we use.
That's right.
Smooth
So
and
techniques
random
of
undersampling.
undersampling, oversampling,
Yeah.
and in particular SMOT, which tries to impute data, which SMOT tries to. So undersampling and oversampling are self-explanatory. You undersample from the normal, you oversample, or you do things like that. The other is that you literally try to generate more data, more of the anomalous data, or the class which is in the minority. You try to do more of that. The trouble with doing that, of course, is there is a presumption that if you have anomalies, the in-between spaces between the anomalies are also anomalies. And that kind of assumption begins to break if you look at situations A and B. You would agree that if you start filling the gap between A and B with more synthetic points, those points are actually not anomalous, right? They will intersect through very normal regions in this graph. Do you see this? If I connect A to B and I start popping up points here, those
Yes.
yellow points, they run the risk of not being anomalous points, isn't it? Right? Do you see the problem with that?
Yeah.
Yes.
Yeah. So that is why Smooth, it works. It's very good, actually. It works quite effectively in taking care of class imbalance. Till the imbalance is extreme and the data is really spread out, right? But then it becomes counterproductive sometimes, right? It's not the best technique. It will give you some mileage, but after that, you'll start hitting a wall. But nonetheless, having said that, it is still possible to take classifiers, use class imbalance techniques, right? And get a certain degree of performance, as you will see in the lab. You can get certain amount of anomaly detection using classifiers. So now we have done two kind of techniques. So unsupervised learning are like things like a clustering, KNN, they're taking the median or sort of median or average distance for the k nearest neighbors, right? And then plotting it out to detect anomalies. And then we did the supervised manner in which you essentially create some form of classifier that will distinguish between this. Now, between these two extremes comes a very interesting region of sort of a semi-supervised learning. And it's a continuum, something is closer to unsupervised, something is closer to supervised. And there's a whole host of techniques that we can deal with, right? And we will deal with in a little bit when we come to the deep learning part. And even here, let me do that. So before I move on from this, let me mention two very popular techniques that are used that has been used for many, many years. Those two techniques are, one is using support vector machines, one class SVM, one class support vector machine is one technique. The other technique is called independent forest. Am I getting it right? Oh gosh, it's not random forests. I think it is called
Isolation forest.
Isolation forest. Thank you. Isolation forest. The word was escaping me. And so I'll explain both of these. Let's start with isolation forest first, because it's the simpler of the two to explain. What you do is, suppose you have data. So let's go back to the same data. We have this envelope of normality. And let me put the data points that are anomalies in red.
And Asif, just to clarify, so right now you're sticking to classical methods only, right?
Yes, I'm giving you a background on classical methods so that these are important, by the way, guys. Yeah. So I'm just quickly reviewing that. And unless you have come to my prior workshop or have read independently, you may not know this. It's worth knowing this before we move to deep learning today. Right?
I have to read up.
Come again?
No, I have to read to catch up, but I'm just following along. Yeah.
That's right. So this is your box. Let's take two-dimensional data. This is your R2 box. This is your bounding region, right? Let's say this is your outer bounding box. Now, here is what you start doing. This is very similar to random forest. So let's say, if you recall, forest. What do? There we create an ensemble of forests, of trees. Right? If the word ensemble, more colloquially, lots of. Right? A collection of trees. We'll build a collection of trees. Now, if you remember, how did we grow a tree? Well, there was this whole fact that you would project down to a lower dimensional space, right? A feature space. You would take random, projections or random subspaces. You would do bootstrapping and all of that. So forget that part. Let's just go, once you have taken a sample of the data in random forest, how would you build a tree? So what you would do, suppose this is feature X1 and X2, you would find the split point along either X1 or X2 axis that gives you the maximum information gain, isn't it, guys? The criterion for splitting was maximal information gain. And I hope you guys remember this from our prior discussions. Right? So you can use entropy, you can use Gini impurity index. One way or the other, you want to have a situation where before and after split, we have the greatest, let's say, reduction in entropy once you split, right? Total entropy, for example, if you use entropy. So you try to create the best tree that would fit a data. But in isolation forest, you actually do something quite different. It's a little bit simpler. You forget all this. You don't do any of this in isolation forest. You say that, all right, pick a random axis. Let's say we pick x1. Pick a random point and just go split it. So maybe I'll pick, let me just go pick this point. Are we together? I split it. Now you have these two regions. Go again, randomly split it anywhere. Randomness is the most important thing. Let's say I split here, right? And this one, I don't know, maybe I'll split here. Then again, I split, let's say here. Then again, I split here. And again, I split here, things like that. Now, what will happen is if I go on splitting like this, and in this region, because there is a lot of data, you stop splitting if there are too few points in the region. So what will happen is you will end up with a lot of splits. Things like that. As complicated as it can make. Something like this. Now, when you look at it like this, through this mesh, do you observe something? You realize that points that are inliner, they belong to very small subregions that you reach by successive layers or successive sequence. A lot of splitting takes you to the white points. But observe that the red points, they tend to be, you easily get them with a very few splits. You know, the big regions, the regions that were created without too many splits are the regions that contain outliers. Do you see that, guys?
Yes.
Yeah. So what happens is that if you, now this thing, if you represent it as a hierarchy, there was a region R0, R1, R2, then this more and more regions R11, R1, 2, R2, 1, R2, 2, and so on and so forth. So what will happen is that, and let me make this tree much deeper. What will happen is all your inliner points are somewhere here. And all your outlier points are a little bit high up in the hierarchy. Let's say that there was another split here. Some, you know, they are achieved. Well, I just screwed myself because I used up all of the spaces. Let's say that I'll just add a third. It shouldn't be like that, but okay, I'll add a third. What happens is that these regions, this point, it will be hanging off a node, a region that is high up, right? It won't get through splitting. So maybe I should redraw it. Okay, so let me just put it this way. Here is this point, right? And here is another point. And sometimes you can have, I'll get rid of one branch somewhere. Let me get rid of this branch entirely. So there may be a point here, and there may be a point just here. Right? So you might end up, and maybe there are 2 points here in this region. And this region is just 1 point and so forth. So you end up with small regions which are empty, except for a very small number of points, and you can't split it any further because you don't want to split it, right? And so if you look at it, the outliers have a shorter path to the root, isn't it? in other words, you get to them with very few splits. So this path, for example, is much shorter. This path is much shorter. This path is much shorter compared to this path. You can see that inliners tend to have much longer paths to the root. Number of steps, number of edges, or number of parents you'll encounter till you get to the root will be much higher, and outliers tend to have less. So that is the basic idea. What isolation forest does is it creates a forest. In isolation forest, you create an ensemble of trees. Each tree has random splits. And then for what you do is for each point, each data instance xi, compute the average path distance, path length, let me just say distance from the root across the trees, right? Find this average value, and in some tree it may be a little closer, 2 steps away, some tree it may be 3 steps away. For each point you can do that, and now all you have to do is, you have a one-dimensional entity, isn't it? For every point you have a distance from the root, and now you can plot your distances, and you can decide where you want to declare it to be outliers. Right? At some point, you can say the outlier score, I'll put it at 0.5, and now you're looking at outliers and hard outliers and so forth. Do we get the concept, guys? So this is a very simple idea, and it's a modification of random forest. In fact, a simplification. You don't use any of these information gain and Gini or entropy or any argument like that. You can do like this, and you'll have your outliers. I hope you understand what I just explained, guys. Tell me that this was straightforward and easy.
Yes, Asif.
Understand.
Yes, great. So then there is another one which is a little bit more abstract. It is the one class SVM.
So Asif, so instead of like splitting it along the axis, if we split it along the angle, will that also help, or?
Yes, so people have done that. It is called random. See, any one of these algorithms have many adaptations, many papers have come out. I do remember somebody saying that for this whole business of random forest, you can get better results if you are not always parallel to the axes. If you go in random directions, you get much better results. And I'm sure that somebody else must have shown that the same is true for isolation forest.
Yeah. So that's I think that's called like the extended isolation forest. Like if you, instead of axis, like you split at an angle.
Okay, I see. Nice. So anyway, so there
I
we
have
are.
one question. So why did you split the red regions only few times and the white regions so many times? I mean, what was the logic behind it?
The reasoning is, see, look at this point A. You realize that this was split number 1. Let's say that there's split number 2, right? This is split number 2. But by the time you come to a point like this, let's say a point like B here, you realize that it is in a very tiny region. Like suppose you say I'll stop splitting when my region has no more than 3 points or 2 points, right? You realize that any inliner, because it has a lot of neighbors, you will have to do a lot of slicing, a lot of chopping of the region till you have a little box around the region, around that point, which contains, let's say, only 3 points. Do you see that, Rita?
Yeah, so it's basically the same density or same number of points. Something.
Yeah, that's right. If you just say my stopping criteria for splitting is I need no more than 3 points. So what happens is for inliners, you'll have to keep on chopping. And, and so any inline point will be in a tiny box, which has been created after a lot of chopping. What it means is that in your region's tree, this tree, it is way, way down somewhere.
Yes,
Right?
yes.
Whereas what happens to outliers? Oh, they get chopped off and have their little isolated little boxes pretty quickly.
Yeah, yeah. So after that, it is clear, but that point I missed. Yeah, why the splitting was so there on the red points.
That's
Okay,
right. That's right. Yeah.
thank
So
you.
that is that. I suppose I should have repeated that, but that's how you stop, for example, in splitting in decision trees. Right.
Okay, thanks, Asif.
Yeah. Nice. So we now come to the one class SVM. In one class SVM, it's a little bit more abstract, so I'm not so sure I can do complete justice to it. But the way you do that is, it is very different to it. You don't show it the anomalies. And therefore, it is not called an, you don't show it the outliers at all. And that is why, strictly speaking, one class SVM is not called an outlier detector. It is instead called a novelty detector. So the way the novelty detectors work, whether it's one class SVM or others, and the way they differ from outlier detectors is in an interesting way. You only show it the normal data. Are we together? So suppose you have a way of getting clean data which has no anomalies, which has no outliers. You just show that to the SVM. And SVM, in a very abstract way, says if this is the normal data, and what is the minimum? Like, how do I shrink wrap it? Says that anything beyond it is anomaly. Are we understanding that? So suppose you give it a data which is normal, it will basically try to create a decision boundary kind of a thing. It will try to shrink wrap it and say, okay, if you now give me a data, all I care is whether it's inside this closed region or outside it. Right? So suppose I get a data here now. Afterwards, after the one class SVM has been trained with only novel data, with only normal data, then you give it a point like A, it will say, well, it's a novelty. Right? It is not, it doesn't sort of meet the definition of belonging to the normal class. Right? Therefore, the one class reference to the class of normal data, class of normal data. Is the idea simple, guys? Are we getting it?
Yes.
Yes, Asif.
Yeah. So here the limitation is with one class SVM and with all novelty detectors, you have to be careful. Your data has to be clean. It cannot have, the training data cannot have outliers. Right? Because if it does have outliers or anomalies, then the SVM will learn that too and try to consider it normal. So you have to give it this. And when you do that, actually, so long as you give it the clean data, you'll be rewarded by a pretty good novelty detector, right? Anomaly detector. It works quite well, actually, right? So that is the point of using one class SVM. So for example, try this on the credit card fraud data set and see what happens. Okay. That is that. I think enough of classical methods, or should I go on with a few more?
Asif, one quick question on the previous one, the isolation forest.
Yes.
So you explain the intuition right now with a two-dimensional data set.
Mm-hmm.
Right? In the two-dimensional data set, when it comes to randomly figuring out, where a box should be,
Yes.
it's a choice of picking, a point on one of the axis and a point on the other axis. When this problem becomes multi-dimensional, there has to be a logic around which combinations are first picked, right? In terms
It
of,
doesn't matter. I'm saying pick an axis and pick a cut point and go build your rectangular volume space.
and so it's
Divide the
purely
volume.
random. There is no guidance in terms of which
There is
dimension.
absolutely no guidance. The only guidance is when should you stop splitting.
Hmm.
And that guidance is that stop splitting, choose a criteria, maybe at 3 points you'll stop splitting.
I think where I was, the question was more like this. Let me rephrase the question there, Asif. So X1 is a feature, X2 is a feature, right? We don't have any relative importance between these features right now.
No, you don't have.
Yeah, okay. Yeah.
You don't have that. And so what happens is that, see, sometimes, and that's the reason you use ensembles, one of the trees may be unfortunate and it may just do it badly. But most of the other trees will do it right. And so on average, A will have a much shorter average distance to the root than inliners, B.
Mm.
Right? And it comes out pretty well. Isolation forest is actually fairly successful. It has been one of the most successful strategies for anomaly detection, to such an extent that when you guys, let's say that you go and interview, it is quite likely that if the company does anomalies or outliers, they will ask you some question on isolation forest in the interview.
Right. Thank you.
So now isolation forest is a true outlier detector. Right? It detects anomalies as outliers. Whereas the one class SVM is a novelty detector. Right? You have to give it only the normal. So it creates a definition of normality. You see that? It says, now I understand what normal data is. Are we together, guys? Right.
Yes.
And so it does that. And so we'll see this in the lab. It's a very successful approach to doing it. Right. Now,
So Asif, is it still like supervised learning or this is semi-supervised?
yeah, that is it. See, what has happened is, it is, you have labeled data. So there's a bit of supervision, but the actual shrink wrapping is a definition of normality, which there is no more labels once you are training it, which is the unsupervised part. So typically this is called
Okay.
semi-supervised learning, right? Or I think it should be.
Asif,
And
one quick question. Sorry to interrupt you. So, how do we ensure that the normal data without any anomalies is fed for novelty detection in
exactly. So that is the labeling part, Sudhir. See what that's the limit. That's what makes it's very effective, but it makes it expensive because now somebody has to take a sample of the data, sufficiently large sample of the data, and from that inspect and throw away the outliers. Some human being has to sit in judgment, know that these are outliers and throw it out, and create a reasonably big sample of normal data so that the one class SVM can understand the concept of normality. It can shrink wrap a region of the feature space as normal.
Okay, got it. Yeah.
That's that. That is the thing. See, whenever you get to some form of label data, like, needing a supervised, any part of it is supervised learning, even partially, the costs go up. Yeah. But generally, it also means that the performances go up a little bit, quite a bit. Huh? So there are more techniques, guys. You can apply many such ideas, very simple ideas to detect anomalies. And there has been a fairly large literature of anomaly detection using classical topics. Some of you have been through the boot camp. If you remember, we did these things in the lab. Do you guys remember? We did isolation forest and novelty
Yes.
detector both.
We also did the LOF, local outlier factor.
Local outlier factor is a metric, yes.
Yeah.
You can find that for points, right? So for density-based clustering, for example, you come up with the LOF factor and so forth. So yes, we have these techniques. Now what I would like to do, in the interest of time, is move on to deep learning-based methods. Deep
Asif,
anomaly. detectors. And this takes a slightly different frame of mind because these are actually a little bit bigger ideas. So before I go into it, just a question. It's a little bit early. What we should do is, let me just ask if there are any more questions because I'm going to move past this.
Asif, would you have links in your on your website for additional
Yes,
literature?
I will. I don't know if I have already added an entire section on anomalies. If not, I'll add it.
Sure, thank you.
Yeah. And so there are some very good papers and review papers. One of them just got published in December itself. That's the most comprehensive review of anomalies in deep learning across the board. I'll post all of these review papers. Any other questions, guys? So how many things we did? We did the Tukey's method for one dimension. We did clustering methods, especially dbScan is a really good one. It automatically comes out with outliers and the LOF factors and so on and so forth. We dealt with the fact that other clustering algorithms can also be used. We used the concept of just the size of the cluster being able to tell whether some cluster of data is anomalous. We also dealt with the taking kn and k nearest neighbor distance, average distance to the k nearest neighbor as a metric, as a distance metric to create a one-dimensional measure now on which we can apply all sorts of arguments like your TK argument to come up with the anomaly score. We did the concept of the anomaly score. So whichever algorithm you use, just to unify it all, you tend to come to an anomaly score. Then we did the isolation forest and we did the one class SVM. Isolation forest is based on the idea that outliers tend to have shorter paths to the root. The regions in which they belong to are not reached by too much splitting, whereas inliners can only be reached after you have really split the regions into fine little boxes, right? Multidimensional boxes. That's the concept behind isolation forest, a simple idea. And then you take an ensemble of it just to make sure that you don't have errors, right? You have a good robustness there. One class algorithm is a novelty detector. What you do is you take only the normal data and you let SVM then discover the one class, shrink wrap it in a sense, right? As the definition of normality. And then whenever a new data point comes, it falls into the shrink wrap regions of yours, then the SVM will declare it to be, by the way, yes, here it is looking like one region. It could be multiple regions in the feature space. So it has those, anything interior to those regions are inliners, anything outside of it are different degrees of outliers, right? And one class SVM also does this degrees of outliers, once again, like TK, the soft outliers, hard outliers, and so forth. It creates a definition, again, of anomaly score that you can use to figure that out. A lot of this will become very real when you do the set of labs we are going to do on Wednesday. So I'm about to get into deep anomaly detectors, guys. Would you like to take a 10 minutes break before we continue?
Yes.
Yes, please.
Yes.
Let's do that, guys. I'm pausing the recording. And I'll see you guys in a few minutes.
Back at 8:30.
Yes, let's not take more than 10 minutes. We should be back by 8:30. All right, guys, can you hear me? It seems everybody has moved on to the break.
Yes, Asif, we can hear you.
Nice. I suppose I'll wait 2-3 more minutes.
So I have a doubt. Asif sir, are you there?
You have to be a little bit louder, Harini.
Okay. Sir, can you hear me now?
Barely.
A little quiet.
Okay. Give me a second. Okay. Now?
Yes, much better.
Okay. So when we do KNN for anomaly detection, but K is a hyperparameter, right?
Yes, it's a hyperparameter.
Then not every point could be in a cluster, right?
Yeah, so there will be error rates. See, what happens is if you take 5 nearest neighbor versus 2 nearest neighbor and so forth, whenever you do KNN, K becomes a hyperparameter. And so at the end of the day, you have to do a hyperparameter search for the best value or hyperparameter optimization for the best value of K that detects most of your outliers. I mean, has low false positive and low false negative rate.
Okay.
Right.
So it's not a straightforward approach then.
Yes, it is not.
Okay.
It is not. See, it's a fact of life. Most machine learning algorithms, unfortunately, they have a hyperparameter, some or the other hyperparameter. Right?
Okay.
Isolation forest, for example, at what level do you stop splitting? How many trees do you build? Right? Likewise, how deep do you go, and so on and so forth. So, in the case of density-based scanning, DB scan, what is your, remember the two hyperparameters was epsilon, the radius of neighborhood, and the number of points that must be within that neighborhood for it to be considered an inliner point, so that you can do directly reachable and indirectly reachability arguments.
Yes.
So everything has hyperparameter, or almost everything has hyperparameter. Very few algorithms are free of them. So see, in real life, at this moment, you're learning a broad spectrum, the whole range of machine learning. In practical life, when you work in the industry, your life will be limited to just 2-3 types of data and just 2 or 3 analysis that you will be doing. And sometimes just one source of data, and the data keeps changing, and one analysis, and you will be spending like 5 years on it.
So Asif, it will be like an outlier?
It will be like an outlier. I don't know. This is the norm, actually. It's a normal. Most people spend the greater part of their practical life, if you work in product development companies, or with just one algorithm, probably one type of data, which keeps refreshing and whose patterns keep changing. So you have to keep tweaking your model. And you are somewhere between good enough predictions for business to fly, and yet in many areas not good enough for some other functionality to happen. So you keep on pursuing greater and greater performance in that algorithm, in that problem, and you keep bringing in more and more algorithm, and for every algorithm you keep tuning it a lot. Yeah. You spend a lot of time hyperparameter tuning. That's why hyperparameter optimization is such a big topic, and we'll deal with that next time. The fact that we can do automated machine learning with its and a hyperparameter tuning optimization automated is a significant part of it. Right? It is a game changer these days. right? And if we can get it right, and we are beginning to get it right now, what it means is you can, instead of hiring people who are very expensive, a typical engineer in the United States, the outer financial box to hire a data scientist in US is about $250,000, right? 250, including the, the office facilities, the health insurance, the taxes, employer taxes, and everything put together. Let's say 250 is the average financial burden. For $250,000, $250,000, you can buy a huge amount of hardware. Right? Typical servers cost about $20,000 or $40,000 for very powerful servers. So you can buy a lot of machines. And so if you can scale it out in machines and make the machines do finding the best hyperparameters in an optimal way, you save on a lot of human and expensive labor.
Okay.
Anyway, we'll talk about it next time.
Thank you, sir.
Yeah.
Asif, one question on the previous topic before we move to the next one. So in your practical experience, I'm looking for some insight from you. So when it comes to label data, right, it's a hard one. It's very expensive to get the label data. Now, for something like anomaly detection, without good label data, you can't actually build that, right? And if you
I'm
take
sorry, say that again.
to do anomaly detection and build an algorithm, build a model to be able to do anomaly detection, you need to have a classification which says these were anomalies and these are not, right?
Not necessarily, actually. In fact, remember I said unsupervised learning, for example, clustering, right? Just by knowing that some clusters are 2 orders or 3 orders of magnitude smaller. Let's say that most clusters have 1,000,000 points and you get a cluster which has only 100 points. What can you tell about it?
So then you go back and re-examine that cluster to then classify that cluster as an anomaly cluster.
Exactly. So to find anomalies, there are unsupervised learning methods like clustering, and there are semi-supervised learning algorithms, and there are supervised learning algorithms.
Okay.
Now,
I think you answered my question. I was looking at, is there a way to go back and re-look at the data to bring the experts back to look at a cluster and say, do you think this cluster is an anomaly?
you do that all the time. You do that. You take those clusters and you sit with subject area experts, right, domain experts, and ask, is it?
Okay.
So whenever you do machine learning, remember that it's a very iterative process. Any big project, right, it spans multiple years. And so you do keep pulling in subject matter experts. And sometimes the subject matter experts belong to your clients. And they will weigh in and say, yeah, this is, it's catching it, it's not catching it, and so forth. Right? Especially for fraud detection. They can tell that, sometimes the boundary is very unclear. Let's take an example. There is a doctor who tends to do a lot of tests, right? Now it is unclear whether he's doing a lot of tests to rake in, money, because those tests are expensive and procedures are expensive. He does a lot of procedures every time you visit him. Is that person being very thorough, or is he, making a lot of money? And sometimes it's a judgment call, and two subject matter experts may differ. One may say this is normal, one may say it is not. I say that because I actually worked on that problem in California. There is a huge, for example, well, countrywide apparently, somebody had brought up this matter. Fraud in medical billing is huge. So you have to talk to domain experts always.
All right, thank you.
So I think that's the reason they're going from ICD 9, 10 to 11 now, so that they can detect fraud.
Yes. What Anil is referring to is international code for diseases. Whenever you fall ill, there's an international standard. If you have flu, there is a code for that. If you have runny nose, there's a code for that. If you have, something like that, broken leg, there's a code for that. And these are the ICD codes, and they have been going through various revisions. And what Anil is referring to is that there's a new revision coming up.
Must be going a little more fine-grained. Yeah.
Yes, they're going more fine-grained. And whatever in response to a disease, whatever a doctor does, there is a CPT code. There's a like procedure, whatever procedure that you apply for treatment, there is a code for that. And it is, the billing is done by the CPT code, and then the CPT code has to be associated with the right ICD code. And if the alignment is not there, clearly you see fraud. And so those are the obvious ones you can quickly catch that something is off. But still, see, all of in real life, there is always a gray area. And you literally have, just like you do an ensemble of trees, you have to do an ensemble of subject matter experts and see where the majority vote is going to decide or tune your algorithms at the end of the day. Quite often you have to do that. So you guys must have noticed that when you get your credit cards, some credit card companies are very trigger happy. The moment they see you do transaction outside your city, they will immediately block it and send you a message and saying, if it is you, click on this and try the transaction again. They're very aggressive and they're a nuisance. Some credit card companies are much more permissive. Right? I find that when I'm traveling, it is safer. In my case, I realize that American Express tends to be much safer to use. They are very travel friendly. But then I also take the trouble to call up each of the credit card companies and tell them that these are the cities I'm traveling to, the security department, right? Otherwise, it's quite painful. You are in a foreign country, you're traveling, and your credit card is being declined, right? Simply because it is being detected as fraud, and then after a little while you notice this message on your phone that says, do this, and then they will, or call us, and then they will unblock the card. Have you guys noticed that? Has anybody else experienced that?
Yes. Yeah.
Many times.
So that again brings up the whole question, right? That it's a judgment call. Where do you draw the line? Where do you call it a fraud, a potential fraud? Where is it an anomaly and when it is not? If you go to the neighboring city, is it an anomaly and do a transaction? How far do you have to go before it's called an anomaly? So those are subject matter experts' decision, and no one answer is correct. It's sort of a gray area. All right, I'll resume the recording now, guys. In the first part of this session, we talked about the well-known anomaly detection algorithms. They fell into the class of outlier detection and novelty detection. Right? There's subtlety between the two. Outliers, you give the data, all of the data, the normal class as well as the outlier data, and you let it do that. Novelty detectors is a little bit more involved. You only give it the normal data to train it, and then it detects novelties in the data. So we went through a slew of examples, clustering and k-nearest neighbor and isolation forest and one class SVM and all sorts of arguments. And there are many more that you can do. The literature is vast and rich. By the way, there is an excellent book by, I believe his name is Charu Agrawal, who has written a book literally called Outliers. I will post a link to that. If you are in this field, if you intend to be in this field of fraud or in any way anomaly detection, I would really recommend that book. It's more a reference. It's perhaps not the best book to learn from, but it is being considered very highly in this field. And reading it once at least is a must if you are a practitioner in this field. It's very readable, and after you get the main ideas, once you know your algorithms, you're just seeing those algorithms being applied to outlier detections. Okay? I'll post a link to that. Now, I will talk about deep anomaly detectors. See, deep learning has had a profound effect in many, many areas of machine learning. You know, it has taken the state of the art forward. Many problems it has taken the art forward. Now, when you think about deep learning architectures, the very first thing that may come to your mind is just think of it as a classifier between anomalous and normal points. Then generally the classifiers with a deep learning architecture, deep neural architecture, tend to outperform other architectures. Not always, but quite often tend to outperform. Therefore, it's our duty to at least try that. And then if you want, you can marry it with other class imbalance techniques and so on and so forth, and see what results it gives you. Right? You get a huge improvement just applying deep learning, deep neural network-based classifiers to this. But then, so that is one technique, and I won't talk about that because we all know how to do that. Use deep networks for classification. That is good. But now I'm going to talk, so I'll leave this thing aside. There's hardly anything to teach here. I will focus on two specific things that has had a large amount of success in anomaly detection. In fact, it has really moved the state of the art forward in many, many problems, the state of the art performance in many, many real world problems. So these are two different neural architectures we'll talk about. One of them is called GAN, Generative Adversarial Network. And the other is called autoencoder. Right. Now, some of you I know have missed some of the sessions. So if you have missed either of the sessions, I would strongly advise you to go to the course portal, look up the associated videos and review it later. At this moment, I will give very quick summaries of these two because I expect most of you have attended the lectures. Nonetheless, I will give a summary of that. So let me start with GAN because that's what I taught first. In a GAN is roughly this. It's a cat and mouse game between a fraudster and a cop who is trying to detect it. So imagine that there is some real data, some real. So one basic intuition could be that you have a pile of real data. Imagine that it is, let's say it's coins, right? If you think of each data instance as a coin, it's data. So X comes in, right? Xi comes in from there. So what happens is that you can give a particular neural architecture. I'll just mark it like this. The discriminator, the police, think of it as the cop or police, right? It's called the discriminator. Its job is to tell the real from the fake. And then there is a guy who is freely, obviously, trying to make counterfeit currencies, counterfeit coins in some sense. He takes a random, let's say Z, right? Z is taken from some random. Either you can take it from normal distribution, or you can take it from just uniform random, right? Make your pick, some sort of a random data, and it has the ability to take random junk and transmute it into a coin GZ. So let me just call it X prime is equal to G of Z, some transformation you apply and you give it to this discriminator. So the idea is that the generator tries to make as legitimate a coin as it can, as good an imitation of a counterfeit coin as it can. And the job of the discriminator is to be able to tell the genuine thing apart from the counterfeit, right? So it's sort of an adversarial game between the forger and the cop, right, or the expert who is doing the discrimination. And so what you do is you give it some real data, and the discriminator says, okay, this is real. You give it a sample. You say that this is real, label data. This becomes your label data, whether it's real or not. The discriminator gets trained. And now what happens is, in the beginning, the generator will produce junk. It won't look anything like the coin of, let's say, of your country, let's say the US coin, right? And so the discriminator will be easily able to tell them apart. Then what happens is you back propagate that loss here to the generator, and you say, aha, I got that wrong by a wide margin. Now, what do I do for my, how do I, change my, this weights in such a way that the next time I'll produce a little bit more realistic coin. And so you keep doing this. The discriminator keeps getting trained and gets better and better in telling apart the counterfeit from the real. And the generator becomes very good as it can be, in being able to generate very realistic coins. So at the end of it, when this game stops, the beauty of this is you end up with a generator which now can generate a lot of fake data, which is realistic. Or if you think in terms of coins in this metaphor, then it can perpetually generate free money now, free coins now, right? And all of those coins will be extremely good counterfeits. So you can pass them along in the nearby, I don't know, 7-Eleven or something like that, right? Those are one of these stores, convenience stores, and wherever it is that counterfeit money is floated usually. Right? So this is your generative adversarial network. Now, the magical thing here is this generator, or the generating function. You take Z, which has been sampled from some sort of a random process, right? Stochastic process. It could be a normal distribution or a uniform distribution, or it could be anything you can pick. Doesn't matter. A stochastic process, right? Some random, let me just say a random process from a random distribution sample. And then just GZ is magical. It is able to take this random noise and it is able to transmute it into a realistic coin. Right? Effectively. That is the power of this. And that's why these are called generative models. It's a generative model, right? Because at the end of the day, you can use the generator to go on making money, right? Or fake coins, counterfeit coins. So this is your generative adversarial network. Now, this is obviously a very quick summary. I wouldn't go too deep into it. Any questions, guys, in this little quick review? Do we recall all of this?
Yes, Asif.
So one question, Asif.
Go ahead.
So in this context of fraud detection, the D is the one which is getting trained and...
No. I haven't come to fraud detection. I'm just giving you a review of GAN.
Okay.
Right. So I will relate it to fraud detection, but in a little bit. it gets quite interesting actually how you relate it to fraud detection. It's a surprising twist to the plot here. Yeah?
Okay.
So if you think of this as a game between the thief, the counterfeiter, the forger, and the cop, there is a very lovely twist to this whole thing. Now, let's think in terms of autoencoder. The autoencoder is typically the undercomplete. I'll just take the undercomplete version. It doesn't matter, the same argument applies to, and now I will just use representation, this, and a mirror image. So this is, let's say what you do is X goes in, it gets transformed into a hidden state, let me just call H, where H is encoder, this part is the encoder, this part is the decoder. The encoder produced encoder is a box. X goes in, a hidden state, H comes out. That hidden state is some function, of X, some nonlinear function, some highly nonlinear. X being the input. And what you do is obviously the way you realize that highly nonlinear function is by having many layers, typically of either convolutions or MLPs, multi-layer perceptrons, dense layers inside it, right? So there will be, I won't draw the figure to complicate this picture, I'll keep it neat here, but you can realize that there are many, many layers inside it. That's why sometimes people use the word stacked autoencoder. In other words, there are many stacks of layers inside it. Those layers could be convolutional layers or MLP layers, or FIFO layers inside it. It's quite common. And you guys have seen the code. We did the lab using both convolutions and standard MLPs. Multi-layer perceptrons. So that's that. Then you have another function G, which is in a sense the inverse of F, right? It managed to reconstruct. It is some function that manages to reconstruct this as closely as possible. So by creating a bottleneck, you come up with a hidden representation of your data, right? A nice hidden representation of your data. The loss function that you use is this x minus x prime, let's say squared. In some sense, I'll just use a vector notation, right? So let me use more of a matrix notation just to say that this is it, right? In a matrix notation, which is basically the sigma I xi minus xi hat squared. Right? This is it. I'm just writing it as like this. This is the reconstruction loss part. We call it reconstruction loss, right? And it is just a mean, like if you divide it by number of data points, of course, it becomes the mean squared error, MSE, right? Usually, when you are doing real value data, let's say image. On the other hand, if you're doing discrete data, then you can change this. And this is one of the points I think I didn't mention. The loss function, the main point, the reconstruction loss, need not be mean squared error. If you're trying to reconstruct input, which is categorical inherently, then you can use, of course, your cross entropy loss. Right? So Either way, then of course you put a softmax in the end and you use a cross entropy loss. But typically people write this implying that with the understanding that if you're doing categorical inputs, then you will sort of implicitly understand that your loss term will be reconstruction loss will now move on to the cross entropy. Now, this is the basic autoencoder, and then we always have an extra term in the in many, I taught you many variants of it, a regularization term, omega, regularization term. And that regularization term could be, omega could be based on which class of autoencoders you're dealing with. Omega, let's say, for this, let's say for just L2 regularization, simple. This is quite literally that, your weights. You are doing a L2 regularization is, as you know, the standard, or L1 or L1, L2 regularization. You can do whatever you want, right? You could put it like this. Then, by the way, there is I don't think I taught you, we are talking of the L1, L2 regularization. Sometimes what people do is that we write the loss function in this. You will see in the literature, in the autoencoder, we do the log cosh autoencoder. What it means is that you replace this reconstruction loss part with the log of the cosh of the reconstructions. So what it does is, in a simple way, it has the effect that when for small errors it uses L2, and for big errors it tends to use L1 or something like that. I forget what the exact details are. So there are many variations. Autoencoder. So I'll just leave the word here in the notes. Log cosh. And there are many variations of the autoencoder. Then we talked about the contrastive loss autoencoder, if you remember, which was stable in the presence of perturbations. And what we did is that we looked at the gradient, right, of the Jacobian, right? We looked at the gradients here, gradient square. I won't go into the full mathematical expression, we have covered that, but it had to do with the Jacobian, basically, right? A square of the Jacobian in some sense. So that is one, and this is your contrastive loss. Contrastive loss, I believe, or contractive loss, whatever. I forget. Contractive loss. Then there's a third, the more important one that we talked is the variational autoencoder, which we did in more details. If you remember, what does it do? It uses, in the autoencoder, it learns, instead of learning the hidden representation, it learns the hidden representation in terms of mu and sigma of a normal distribution. It says that the entire hidden representation in the latent feature space, you force it to have a Gaussian distribution shape. So the only thing that matters is a mu and sigma that you learn, and then you sample from that, and then you have your decoder part of it, right? And if you think in terms of the omega, basically for this, the omega becomes the KL divergence. It's a KL divergence term, and we won't go into it, but I'm just tabulating it in one place. So there are many variations of it. One of the autoencoders that has recently come and gained a lot of attention, which is based on optimal transport theory. And once again, it's mathematical. Maybe someday in one of the Sunday sessions I'll talk about. It has to do with optimal transport theory and the Wasserstein distance based, instead of a KL divergence, it uses the Wasserstein distance. And it turns out that it outperforms, it's very well conditioned, and seems to outperform all the other, or most of the other autoencoders in many situations. So the state of the art keeps moving continuously. So this is all about autoencoder, but we will keep ourselves for simplicity to this and forget the omega term. Just look at the contrastive loss term and stay with this basic architecture for autoencoders. So let me repeat what I said. We have the generative adversarial network, GANs, whose architecture we just understood, and we have the autoencoder. Are we together? Which tries to minimize the reconstruction loss. So it comes up with a very efficient hidden representation of the input data. Input data, for example, in the MNIST is 786 dimensions, if I'm right. And we did that with what, 8 or 16 dimensions in our lab. And yet we got a pretty good reconstruction and very low reconstruction loss. Do you guys remember that? Right? And we could use it for all sorts of things. We could use it for denoising. We could use it to get sparse and all sorts of things we could do with the autoencoder. So autoencoders are a very powerful thing. And of course, GANs are also very powerful. You can say that, these are some of the most successful architectures, the convolutions, the recurrent neural networks, the attention, the autoencoder, the GAN. These neural architectures are the workhorses, obviously, of the industry to quite an extent, very, very ubiquitous everywhere. So now I'm going to connect the dots between them and anomaly detection. So the thing is, how do we do anomaly detection using it? With autoencoder and GAN. So let's take autoencoder for anomaly detection, right? And the idea, actually, the simplicity of the idea is just quite amazing. Let me take autoencoder. So what happens is that you start, just like with the one class SVM, start with, take only normal data. So once again, the burden is on you to train this autoencoder only with normal data. Are we understanding that, guys?
Yes.
Just with normal data. That is the most important thing. So then what happens is, when you train this with normal data, it will minimize the X hat will approximately be X, isn't it? And so the hidden state representation that it creates will be, it would have learned that manifold, the latent space manifold. People often use this word for manifold. How should I do it? Manifold. What does manifold mean? Remember, think of a bedsheet in higher dimensions. That's your manifold. So what happens is that all of these input points, they tend to become points in the latent space. But those points are not uniformly spread in the latent space. They are sitting, or they are embedded or close to some higher dimensional bedsheet of sorts, crumpled up bedsheet, right? The manifold. Well, crumpled up bedsheet is a very, very rough idea. So curved surface, hypersurface. It is close to that. It is sitting on that or close to that. Are we together? Right. And so in some sense, by making X hat close to X, what it has done is, at the latent space, this latent vector space, it has discovered this manifold. Chi. It is the surface on which, hypersurface, on which all the hidden state vectors are sitting. All the HX are sitting. Are we together? And that is occupying only a part of the higher dimensional, the entire latent vector space. Am I making sense, guys?
Yes.
Right, that is it. So now the idea is that if you train it only with real data, I mean a normal data, what happens when you bring in an anomaly? So let me use Y for, I need a special symbol for anomaly. What should I use? Would it be okay if I use Y for anomaly? Right? So remember, Y we use for outputs. Let me just say anomaly, XA. I feed it XA and you get X hat A. What will happen is this XA, which is anomalous, it will sort of be not exactly on the manifold and a little bit away from the manifold. Then what will this system do? So this is trying to, you take this, it is trying to fit it somewhere here, and it is trying to reconstruct what it thinks a close approximation to XA, the anomalous. But remember, this autoencoder knows only one thing. It is like you have taught it to speak only English. So wherever it sees characters, it tries to speak English or read it as English, in effect, right? It's something like that intuition that whatever you give it, it will produce normal data as output, right? Your data that will come out will be normal. This will look normal, right? Let's take an example. Suppose you have digits 0 to 9, 1, 2, like that, right? But now, instead of feeding that, you feed it an H, an image that is an H, right? What is the best it can do? Maybe whatever it is closest to, maybe it is close to 4 or it is close to 8. It will be close to these two things, maybe. I don't know what else I can think in the digits that it will be close to. So it has learned how to reconstruct the digits. Let's say that you have only trained it with digits. Are we together? So what will it do when you feed it something like this?
It will not be able to classify.
That's right. It will just try to create something closest to this, right? It will enter some space off the charts of this manifold. And the closest thing on the manifold would be these points. And the reconstruction from these points would look one of the normal data points, right? It will look like maybe 4, or it will look like an 8 or something like that. Let's say that you feed it an H. Are you getting an idea, guys? Are you seeing the intuition here, right? It may end up producing one of these, something like this. But now is the fun. You have duped the autoencoder, because now what will happen, if you look at the reconstruction loss, which is the X hat A minus X A, what do you expect this to be? Would it be much bigger?
Yes.
Than for normal data? Isn't it? You fed in H and 8 came out, or 4 came out, right? So you would have a pretty significant reconstruction loss. Now, reconstruction loss is a number, isn't it? It's again a scalar. So you can again have a one-dimensional distribution. Let's say that your reconstruction losses are all something like, I don't know, I'll just create a distribution. Let's say it's here. And then suddenly what you will notice is all your anomalies reconstruction losses are somewhere here. Do you see the beauty of this argument, guys? It's pretty well argued, actually. And that is it. You just train an autoencoder with normal data, and then once it has become very good at minimizing the loss of normal data, it has basically been conditioned. For example, if you think of in terms of MNIST, it has been conditioned to produce 0 to 9, some variance of that. So it is reconstructing from this manifold of normality to that, right? And so you give it something that is off it. The best that it can do is it can pick things close by on the manifold and reconstruct that, right? Decode that from the latent space back to X hat. And therefore, you will end up with a significant contrastive loss. So in other words, the reconstruction loss of anomalies will be significantly more than for normal data, right? So if you were getting very strict, and people don't tend to do, it is more like novelty, technically you would say it's a novelty detection algorithm for anomalies, right? Because you trained it only on normal data and got away with it. So guys, pay attention and ask me if there is any part of it that we didn't understand in this argument.
Asif?
Yes.
Is this actually analogous to the one class SVM we talked about earlier?
Yes, because there also to train, you gave normal data. You carefully weeded out the outliers or anomalies and gave it only normal data. In the same way here, you give it the normal data.
You know how like on Sunday we said, you can probe the deep neural networks and see like what they're doing, like as they're doing like kernels. Is it kind of like this?
Mm-hmm.
Like, did anyone actually
relate it to that paper? Okay.
Okay.
I mean, it's a rather long argument, but if I were to try to relate it to that, I would do it this way. See, there, those researchers are claiming, and obviously the research community still has to weigh in, but the argument seems very persuasive, that deep neural networks are nothing but, in some sense, support vector machines, but with an interesting kernel, a new kernel, right? It is a kernel which is a path integral over the tangent, over the time. Like basically, you take the tangent kernel, right, neural tangent kernel, and then over that you do a path integral, right? So it can do that. But at the end of it, what it does is that the conclusion that they were coming to, or the more significant observation they were making, it therefore follows that deep neural networks do the same thing as support vector machines. They are machines that somehow remember the training data, or at least the important ones of them, the lighthouses, right? The significant ones of them. It remembers some more than others, let's put it this way, the other ones are less remembered. But ultimately, it somehow remembers the training data in the network. But besides that, it is just not an instance-based in which it will regurgitate. It has the ability to generalize. The whole theory of support vectors or the kernel machines is that it can generalize from those instances. So when you give it a point in the feature space, the first thing it does is it goes to the kernel space using the mapping function and finds the dot product to all of those training instances, especially the support vectors, the lighthouses. And based on that, it is able to therefore interpret it. A similar statement, now let's bring it back here. See, what has happened is, if you take your autoencoder and show it only normal points, right? What will happen? Your input, so long as your input is close to, like, is something normal, right? It is within the realms of the normal. What happens is that the latent vector that you produce, because it is made out of essentially the points it has learned, isn't it? Kernels, in the similarity to kernel similarity to points, data points that it has seen, it will produce a latent space, a latent representation along those lines. Now you give it a point that is completely different, right, from what it has seen. So now what happens? Remember the kernel similarity function. If you remember that the argument in the paper is the kernels, the k, right, which is based on the loss at this and the loss at points. I wouldn't go into the full details, but this will, and then you're reconstructing it based on AI, and so I wouldn't go into that. The summation of I, the y is equal to this kernel plus, not to mention the bias term, right? So the outputs are based on the nearness or closeness or similarity of this point in the feature space to other points that the system has seen. But this is way off. And so the performance of your support vectors or your kernel machines will be poor. And to the extent that deep learning can be thought of as kernel machines, its performance will be poor. But that is, the beauty is that that is exactly what you want. You want it to perform poorly for anomalies. Dennis, are you getting that?
Yeah, somewhat.
So the argument is very simple. You take these neural architectures, you train it to work well on normal data, and then you sit back and grin. You throw it a curveball, you throw it an anomaly, and you see it fail, right? You see it come up with a bigger loss. And when it comes up with a bigger loss, you know that this is an anomaly. That's what you do with autoencoders.
Thank you.
Okay. Any questions, guys, in this? Is this argument clear, guys? This is it. If you understand this, you have understood the autoencoder version of anomaly detector. Is it effective? Tremendously effective, especially as you use more sophisticated versions of the autoencoder. Start with variational autoencoder or use the Wasserstein distance-based autoencoder based on optimal transport and so forth. There's a whole flurry. As I said, autoencoders are an industry in their own right, or sort of research area in their own right, not an industry, but a subfield in their own right. So you can keep using and trying different autoencoders, more well-conditioned autoencoders, and you can get better, quite good performance on anomaly detection. They were considered a bit of a game changer when they came out for anomaly detection. But the argument is very simple and elegant. Now, what about GANs? What are GANs up to? So I noticed that we are a little bit running out of time, and soon Shini will say that we are reaching point of saturation. Shini, are you already feeling that?
For now, no.
No, good, because we still have the GANs to do. Here comes something quite interesting, the generative adversarial network. What can you do? Let's go back to the old example. You have a mountain of coins, right? Data. By the way, I hope you guys don't mind my using a very sort of a illustrative but somewhat imperfect examples, or not very accurate or precise examples, because it's a little easier to think with that. Let's say that you have a discriminator, D, you have a generator, G, you take Z sampled from some sort of a random process, let's say a normal process, normal distribution or uniform distribution or whatever, pick your poison here, doesn't matter. But G has the magical, generator has the magical ability to produce something which is uncannily similar to X when it gets trained. Are we together? Right. And so you have a discriminative loss. This is a discriminative loss. This can be a standard classification loss, right? For example, cross entropy. Cross entropy, right? Let me just use cross entropy loss, classifier loss, or classifier loss. Now we are in familiar territory. And the whole idea is that you can keep training the cop and the fraudster, and at the end of the day, what will happen is this will become very good at producing X, realistic coins, right? It will become very good at that. So now see, the way you argue is quite interesting. And so this has gone through many, again, many versions of GANs for anomaly detections have come about. I will just take the core idea. There are many variations of it. Maybe I'll talk about a couple of variations. What you do is you again take only normal data. Because now you want to fool this generator. So what you do is every time you give normal data, this generator will try to fake the normal data, right? Something like the normal data. At the end of it, what you do is you take only normal data. This generator will become very good at faking the normal data. And then what you do is suddenly you come back with an anomaly. And then the X anomaly that it will produce, the generator will be forced to produce. It doesn't know. It has learned to produce, for example, 0 to 9s. And you bring up, let's say, H or something like that. What will happen? Generator has completely not been trained to produce an H. So it will produce the closest thing to H, right? And so what will happen to your classification loss here, classifier loss here? The output that it produces, the XA that it produces, let's say that it's an image, XA prime that it produces, and XA that you have, the anomaly that you have, it's very interesting. So this will be, let's say, the letter H. And this has produced the letter 4, like this. When you subtract these two, in an image-wise, what do you get? You get regions of error, clear regions of error. This. Let's say that I write the 4 like this, just to emphasize. Right? And the parts that will match are. So this part will stand out very prominently as mistakes. Do you agree, guys? Do you see how it works?
Yes.
Right. And so, and not only that, therefore, the added benefit of GANs is not only can it tell you that this is an anomaly, but it can tell you where in the region those anomalies exist according to its interpretation. Do you see that, guys? And so that's a nice thing. You can literally compare these two and tell in a visual way where the anomalies in the image exist if you're dealing with images, right? Or let's say that the coins are images of coins, real and this thing, then it will tell you that these are the places that the counterfeit coin got wrong, right? So this is the basic idea of using the generative adversarial networks to do anomaly detection. Now, while this is the base idea, people have cultivated it quite a bit. And they have gone and created many architectures, creating the state-of-the-art models. I will give you maybe 2 architectures I can talk about, which are interesting. So people have created lovely architectures. I will bring one of them here. These 3 architectures, I wish I could write on them. I can't, or maybe I can. I don't know. All right. So when I put my mouse here, is it visible where my mouse is, guys?
Yes.
Yes. Okay. So this is your basic GAN kind of a thing, the way we talked about it. Now, the first extension that people came is that they created an encoder, which in some sense is the opposite of the generator. they trained it together. So this is called the EG bad. I won't go into too much of it, but basically what you do is you add an encoder layer. Okay, I can't circle it, and you train something opposite to it. Basically, it just helps the whole situation, but the idea is the same. And likewise, there is the latest is the C, which is the GAN anomaly. GAN and anomaly word put together, sandwiched, is GANomaly. Okay? What GANomaly does is something very interesting. It before it gives you the real data to the discriminator, the genuine data, it passes the genuine data through an autoencoder. So X becomes the X first goes into the sort of a encoder part, that GE, then it goes to a decoder part, but when it goes to the encoder, it becomes Z, a latent representation. And then when it goes through GD, the decoder, it is reconstructed as X prime. And then finally you pass it through one more layer of encoder, which is this to produce Z prime, right? And what you do is you have a discriminator that tries to distinguish between the original X and the X prime, right? The usual thing. So all of it gets trained, but one of the byproducts that happens along the way is that in this process, you can also look into Z and Z prime, and by trying to reduce the gap between Z and Z prime, making Z and those two latent representations similar, you end up sort of training this encoder also along the way. But at the end of it, it all comes down to there's a bit of little bit of mathematics and this and that. But the end of it is, why would you do something like that to the GAN? It turns out that by sandwiching an autoencoder in front of a GAN, or into a GAN, you get more stable, a higher quality anomaly detection. So it is not always true. For sometimes B does well, sometimes A is good enough, sometimes C. So there are many, many variants of GANs that people use, they have come up with, that they use for anomaly detection. So I won't go into all of those. Suffice is to say that if you understood this idea that I had here, where was that? This. If you understand this much, you have understood how GANs work, right, for anomaly detection. So autoencoders and GANs are quite often used, and there's a whole, subfields that keep trying to create many, many variants of this. In fact, I can show you one particular thing. Right? Somebody has created with a package and sat down and implemented a lot of these autoencoders. Right. Now, this is just an implementation of the autoencoder. You can use any one of these autoencoders for your anomaly detection. Right? Variational autoencoder, conditional variational autoencoder, then the WA, you have to look at it. So each one of these, you can go and see what they're talking. Yeah, this is the Wasserstein distance, the Wasserstein autoencoder. And this itself has two variants, the MMD and what is the other variant of it, MMD. And okay, so, okay, there's one more variant of it. But anyway, using RBF kernels and using IMQ kernels, but there is one more version that's not implemented here. Then you can imagine this is a long list. You can keep going down this list. Right? The log stash is what I was talking about. All it does is the mean squared error replaces with the log cosh.
So what are we seeing between the left and the right side? Is the
Come
right
again? What is the distinction between the two?
left and right
I
side?
think it is the reconstruction loss. This is the right is the sample, left is the reconstruction of the sample, how well it reconstructs. Right? Actually, yeah. No, okay. No. I don't think it looks like reconstruction. It looks like some of the sample data is given on the left and some of the sample faces generated is given on the right. I don't think they look anything close to each other.
No, as if left side reconstruction looks better images. If you see image icons.
That's right. That's right. Because these are all variational, right? They're generating new data points. For example, this guy wearing a cap, I don't see anybody here doing that. Yeah, I think that is it. I may be wrong. So this is it.
Especially that one where it's really fuzzy and for the WAE, MMD, RBF.
That's right. These are the samples. Actually, I have a suspicion that reconstructions are reconstructions of the input data, and samples, because these are variational autoencoders, they are samples. You'll have to read the documentation. Okay, all the models are trained, the architecture, here are the results. He doesn't give an explanation what is left and right, except saying reconstruction and sample. So we don't know whether the sample is the original samples or it is sampled from the variational.
Output.
Yeah, it is. Yeah, the output of the variational. You can generate from the, just use the decoder part and sample from the Gaussian to generate those.
With that link.
Come
Get
again?
more information. The link.
It's too faint, Kate. I can't hear you.
The link. I noticed the second column has the link.
That is right. Yeah. So we have to probably go to the paper, and we'll have to look into the paper. By the way, this paper, Wesenstein, is a very good paper. At some point, maybe on a Saturday, on a Sunday, I can cover that. This is a lovely paper. It is based on the theory of optimal transport, and optimal transport these days has gotten a lot of attention. So this is the optimal transport theory. It looks as how do you convert one distribution into another. Right, so it's in the same flavor as scale divergence, but it tends to do much better. So I don't see those images. Yeah, it is just dealing with MNIST. It is not dealing with the, yeah. So there's one version using something called MMD. We have to look it up, and the other is the GAN using a generative adversarial network. So it's not clear to me, at least. If you guys can figure out, then whether sample is real sample or they generated from variational autoencoder. So guys, this is it. This is a theory. At least in the lab, we'll cover this much theory. The field of anomaly detection is rich and vast. Deep learning methods tend to focus on pretty much be based off these two core ideas. Right. Any questions?
Asif, quick question. On autoencoders, you have mentioned that when you have a low accuracy rate, right, that's where we detect it's a anomaly detection. That's how it is done, right? So there can be any other factors too?
No, don't use the word accuracy. Low performance is okay. Accuracy is a suspect word because, when the data is so imbalanced as to have anomalies, accuracy of just even the baseline classifier will be extremely high. So you have to look at the precision and recall.
Okay.
False positive, false negative rate. Those are the things you focus on. So how good is the specificity and things like that? So generally what happens is that the broad statement is that deep learning algorithms tend to fare better in many domains, practical domains.
So Asif, this can be extended to even for a language model, right? Like NLP for classifications where you can text classifications, where you can even detect anomaly detection there for fake news.
Yes, yes. So please give me a moment because we are going into QA. I'll stop the recording. And stop the stream.